Hello, welcome to Math 1324. This is Chapter 10, Section 1, Example 5, I think. Anyway, we want to give the domain of the function defined as follows. F of x equals x squared. Now, something weird is happening that we haven't seen before. We're specifically being told, first of all, that it is, in fact, a function. And even if we weren't told that specifically, we would know that because of this equation, f of x equals x squared. And you may be wondering what in the world's happening here. Well, over here, that f of x is just the y variable. So when you have a function, what you can do is replace the independent value, in this case y, with function notation. That's what this is called. Now, what we say here is f of x. It is not f times x. It's not fx. This isn't a television program. So this is just f of x. Okay. Now, the word of often means multiplication. That's not what this is. This is basically a function operator, if you will. The function operator on x looks like x squared. In other words, whatever x is, this is what's happening to it. X is being squared. Okay? And that's really all it is. So this would look like, if we didn't use the function notation, it would look like y equals x squared. And notice that we can only do this if y is just y, not y squared, not y cubed, just y. Okay, so y to the first power equals x squared. And that is exactly the type of function that would be, excuse me, the type of relation that would in fact be a function. Now, let's talk about domains. With domains, for functions in this form, we're going to have different possibilities. So this, if you were to graph y equals x squared, it would just look like a parabola. And that's fine, there's nothing wrong with it. Notice that on the x and y axes, the x tells me the domain. And because this is a polynomial, and a polynomial takes the form of a sub n x to the n plus a sub n x to the n minus a sub n minus 1 x to the n minus 1 plus dot 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 all the way down to a sub 1 x plus a naught. In other words, a linear function, quadratic, cubic, quartic, pentic, hexic, I think, heptic, octic, I don't know, whatever. Generally speaking, if it's got a polynomial for your definition, then the domain will always be all real numbers. And that's how we say that. Now, what we mean by that is on the number line, I can go all the way to the left on the number line and all the way to the right on the number line. But remember, on the number line, to the left indicates negative infinity and to the right indicates positive infinity. That means that I have to begin with negative infinity and end with positive infinity. And that also means that because we have infinities here, we have to exclude using parentheses. Square brackets mean you include. Now, the reason that we have to exclude infinity is because infinity is not actually a real number. We'll never actually reach infinity. So because it's not actually a real number, we have to exclude it from our interval notation, which is what we're using here. And in this way, we have literally written down an infinite number of numbers. It was fast, huh? A lot quicker than I would have expected. Alrighty. Well, there you go. That is the domain for any polynomial function. In fact, there will actually only be two things that limit our domains for at least this particular section. Once we get to logarithms, we will add in a third one. Okay, but for now, any polynomial means the domain is all real numbers. Okay, well, I believe that's it for this example. I will see you all in the next one. Have fun.